All right, so we're recording. We're going to talk about double integrals today. And just quick reminder, we've already talked about something called, here it is, iterated integrals, right? And that's this idea right here. It's a single variable integral of a single variable integral. So a case could be made, and I'd kind of push for this point of view that that's not really a multivariable integral. It's a single variable integral of a single variable integral. It's arguably someone who with the knowledge of single variable calculus could totally understand this argument. Okay, all right. So it has its limitations. A pretty severe limitation, as we saw. Now, it works to compute volume. That's great, but ultimately the reason that it is able to compute volume is that this product right here happens to be something amazingly that we're already familiar with. That was a lucky break, right? We came into this looking to compute volume. We found ourselves right in the middle of the process. This thing called height times length comes up, and oh my gosh, lucky break. We do know what that is. We do know area. We didn't know area was going to come up in this calculation, but it did, and we already understand it. We can make accumulation arguments. Everybody wins. Okay, that was a lucky break. And no such luck if you're trying to understand, say, for example, mass or any other, application that isn't volume, because you end up with, at the exact same stage of the calculation, needing to understand a kind of a quantity that we just don't. And so I can't make arguments such as, the whole sum of the parts, chop it up, add it up. I don't even know what that is. How do I know that it behaves the way that I hope it behaves? Okay, so dead in the water from that point of view. So we start off now, new idea, something called a double integral. Real quick, I do want to start off with a reminder of what single variable integrals are. This is a surprisingly often misunderstood definition. Lots of students get out of single variable calculus classes with the kind of impression that integrals are defined as area under the curve, which, of course, by which they mean area under a graph, right? This is importantly not true. Integrals are not defined as area under a curve. Area, in fact, is actually not even all that important of an application of integrals. It's, as I say here, it's kind of a nice visual aid. I like it, right? But how often is it in the real world, when you're doing an engineering problem, for example, that you need to compute the area of something? It's not really usually the point, right? So how does area relate to integrals? Here's what I propose. Integrals, first of all, are defined as Riemann sums. This is a really important point. Integrals are Riemann sums. Now, if you are asked to compute area, hey, cool, I can take that question, I can turn it into a Riemann sum. And that's nice and all, right? But there's so many other applications that also, when I'm asked to compute, let's say, the mass of something or the population of bacteria on a whatever, etc., work, probability, you name it, you can also turn them into Riemann sums. What you can't do is make a direct, immediate argument that suggests that these kinds of applications immediately are areas. That doesn't make any sense, I argue. Right? So suppose you want to compute the mass of a one-dimensional rod, right? You have this, rod of non-constant density, sitting on the x-axis, and you want to compute how much mass there is in it. Where's the area in that question? There's no area in that question. Area under the curve? What curve? And if you do define, hey, let's look at the graph of the density function. Okay, still, you just made that up. Why should area equal to mass? It doesn't connect, right? It's a total disconnect. Now, what you can do is make arguments that are sort of bending kind of toward almost, but not quite actually making a Riemann sum argument there. And the best arguments that I've ever heard for, why I should think of applications as being areas are by way of Riemann sums. But if you have to go by way of Riemann sums, if you're already here, why not just define integrals as we have here? Integral is that Riemann sum. Let the fundamental theorem compute that, and we win. What's the motivation to then jump over here to area and then, there's just no point in bringing area into it, other than as a visual aid. Right? Area is good as a visual aid. I give it that. So anyway, very importantly, the direct connection to the applications that y'all, as and I'm suspecting most of y'all are probably not math majors, but if you're here in this calculus class because you want to be able to solve applied problems, you want to compute the mass of something or the amount of work it takes to accomplish a certain task or whatever, very importantly, there is a direct connection to those questions to Riemann sums. There is not a direct connection of those questions to areas. So this is why it's really important. Again, not because of ivory tower mathematician purposes, right? But very important so that we can use calculus in the real world. It's very important to understand that integrals are Riemann sums. Okay. Now this is the streamlined version of this pitch. I want to point out that on my YouTube channel I have a playlist called Miscellaneous Topics where I've made various recordings that address questions that come up with in teaching multivariable calculus and things that my experience has been a lot of my students really don't understand as well as they should. And this is one of them. You'll see I have this recording here called What is an Integral? And in this I address various little misunderstandings that end up being important, but various little misunderstandings about what integrals are. So I would encourage you to give it a look. You can fast forward through it if you're totally crisp and clear on all those points. You can click through, fast forward through in a couple of minutes probably. But if there's anything in there you're not entirely clear about, maybe you ought to go ahead and invest 29 minutes and watch that. So anyway, hope you find that useful. Alrighty, so integrals are Riemann sums. Now let's ask the question, what if I needed to do a Riemann sum-like construction, but instead of chopping up an interval into pieces, what if I had to chop up an entire rectangle? What if I had a two-dimensional domain? Yeah.
I'm sorry. What's the note?
So I'm in my chapter 5 Math219 notes, and I'm on page 4, the bottom of page 4. That's right. Yep. All right. Yeah, good. And y'all, good for asking. And I encourage everybody, if you want to know where I am in the notes at any time, you're always welcome to ask where I'm at. Yeah. Okay, so we've got a two-dimensional domain. So whatever it is that I'm interested in computing, and we'll see various examples. I always like the mass metaphor just because I find it physically relatable and kind of, satisfying and easy to understand. So suppose I have mass distributed not like a rod distributed across an interval, distributed across length, where, mass per unit length is the associated density. What if I have mass distributed across an area? And how would I chop that up into little pieces and add up those little pieces? And, well, here you go. Basically, the idea is I would slice and dice. That part's probably clear. There's the slice, and now the dice. I was surprisingly competent at the line drawing. Usually I miss pretty badly. Anyway, chop it up into little pieces. Now there's various work that has to get done as you do this. Notice that as I slice, as I slice vertically, I am also making slices of this interval from A to B, which I already know how to slice intervals from A to B. That part's easy. Delta x, x sub I, no problem. Familiar little formulas. Now notice further, though, that as I slice horizontally, bad color choice. As I slice horizontally, I am also, coincidentally, slicing up this interval from C to D. Now, it's from C to D instead of A to B, but, I mean, if you will, I'm going from a lower bound to an upper bound. It's just an interval. It's really morally kind of the same sort of a situation that we were in slicing up on the x-axis from A to B. So you get an analogous formula for delta y and an analogous formula for y sub j. And all together then, I have formulas for how to identify where I am depending on how far I am along the x-axis and how far I am, I better erase that thing, how far I am along the y-axis. So now that's just details. We're just, formalizing what we mean by slicing up an area as opposed to slicing up an interval. Again, no surprises that we end up with formulas pretty similar to what we already had in the one-dimensional case. So those details set, let's see here. Let me clean up my mess. What we've got then is we have chopped up our domain into a bunch of little, not sub-intervals, but a bunch of little, what you might call sub-rectangles. And it's on each of these little sub-rectangles, not the intervals on the x-axis or the y-axis. It's on the sub-rectangles that I can make easy little arguments, such as if I wanted to compute the mass that's in that little piece, well, in that little piece, it would be mass per unit area times area, because that's how mass per unit area works. There's no funky unit issues like I had here where mass per unit area times length. What is that? I don't even know what that is, right? No issue here. Mass per unit area times area. Mass per unit area was made to be multiplied by area. No problem. Okay. Oh, maybe this is Wyoming and I want to compute the population of Wyoming or Colorado. Take your pick. Right? Or any of various counties out in the middle of nowhere in northwest Texas, right? If you know population per unit area, well, population per unit area times area would tell you how many people are living in that little region. And of course, if you know how many people are living in each of those little regions, you just add up over all of those regions, right? Adding up over the whole. So this is totally analogous to a single variable calculus Riemann sum. It's just that instead of chopping up an interval into sub-intervals, we are instead chopping up a rectangle into sub-rectangles. But the big idea, the strategy of what does this have to do with computing stuff is the whole is the sum of a bunch of little pieces that you can add up. All right, so this is going to be super useful for computing all sorts of stuff. So we need to give it a name and a notation. The notation that we're going to use for that expression is right here. And the name is, this is called a double integral, computed over that rectangle. Okay, this is chop it up, add it up, as applied to a two-dimensional domain. Alrighty, so real quick discussion, if I can get this to erase, a real quick discussion of the notation. I think it's pretty believable that because delta x times delta y was supposed to be computing area, doesn't it make sense we would call its product dA, representing a little piece of area? That's its job. And here we're doing a summation, but notice we have to add up over all the little rectangles, which means we're adding up over values of both I and j. We got to keep track of where we are horizontally and at the same time keep track of where we are vertically, because there's not just in little pieces, there are in squared little pieces. So because we're adding up over two indices, we're going to use two little integral symbols. I think that's pretty plausible. Okay. All right, so here's your definition of a double integral. And it's going to turn out to be useful for all sorts of things. Now, real quick aside, our textbook and others, and the Math219 textbook, where I was writing these notes from, do make more general definitions. They instead of chopping up the intervals evenly, they chop up the intervals irregularly, and there are excellent reasons for wanting to do this. It's just that those excellent reasons aren't really relevant to Math 212. So where the book talks about irregular partitions, just ignore. And likewise, test points, sometimes called sample points. That again, there's powerful, important mathematical reasons to want to do that are not relevant to Math 212. So ignore all of that as well. We're going to be focusing on continuous functions, and for continuous functions, you don't get any different answers no matter how you slice, no matter which points you use. It's all the same. And so, for our purposes in Math 212, what's the point? Okay, no pun intended. All right, so moving along. We've got this brand new tool, double integral. Let's use it to answer a question. Suppose I have a graph, and I want to compute the amount of volume that's sitting under that graph. Right, keeping in mind that the graph is a surface like so, and don't forget I need it to be positive and continuous, just so I don't want to have to deal with absolute values right now. Okay, so there's the question, and look how easy the argument is. If I want to compute the whole volume, that whole volume, I argue, I think this is pretty believable, is the sum of the volumes that I get by looking over individual subrectangles. Let me draw this a little bit differently. If I want to know the volume sitting over the entire domain, oh, come on. Sometimes my elbow hits the little trackpad there, sorry. If I want to add up the volume sitting over the entire rectangle, I can instead say, well, let's one at a time look at these little pieces of volume sitting over the sub-rectangles that I get when I chop up my domain. Volume is an accumulating quantity. The whole of the volume is the sum of the parts of volume. I like to think of this one in particular as being when you order the French fries, right, and they come in the French fries are stacked vertically. I like to think of this as the sum of a bunch of French fries, and if I know how to compute the volume of each individual French fry, then grand total, how many French fries did I get? How much volume of French fries is there? Is the sum of all the individual French fries, right? I think it's a pretty easy, believable statement. All right, so that's what this says, that the whole of the volume is the sum of the little pieces of volume. Now, looking at any individual French fry, how much volume is there in that French fry? Well, it's going to be height, which is f of x comma y, because we're looking at a graph. So z is f of xy. So we get height times, and then I've got to look at the area of the base down here, but the area of that little base down there is delta x, delta y, otherwise known as dA. So, in fact, the volume of any individual French fry is that. Lo and behold, I have a Riemann sum, right? The total mass of volume of French fries is the sum of all those individual pieces. Again, this is exactly a Riemann sum, which by definition is an integral, double integral. Is that cool? Yeah. All right. Now, you could make the case we already knew the answer to that question. We already computed the volume under a graph. We did it with iterated integrals. So what's the point of doing it again? And I'll remind you, we've seen many examples so far, and we're going to continue to see more examples. It's nice to compute something two different ways. among other motivations, if you compute something two different ways, both of the answers that you got must be equal. Right? And that's the big result here. The big result is that now that we've computed volume as a double integral, and reminding you that we had previously computed volume with iterated integrals, the actual punchline here, what we really care about, is that this tells us that double integrals can be computed with iterated integrals. And let me show you how this fits into our strategic diagram. It's like so. I computed volume with a double integral. That's nice. I computed volume previously with iterated integrals. The point being that connects these dots. That makes the connection then between double integrals and iterated integrals. And why do we care about that? Well, we care about that because while we know how to compute iterated integrals, that's single variable calculus. We can compute iterated integrals all day long. Boom, boom, boom. We get to pretend variables are constant. It's just single variable integrals over and over again. Nothing to it. And while we already knew how to compute, how to rewrite anyway, applications as double integrals, if you take away these connections, double integrals aren't that useful because I don't know how to compute them. Iterated integrals aren't that useful because I don't know how to connect them to the real world. The whole point here to the volume computation is to be able to make that connection right there. So that now we have a 3-step process. If you have an application problem, write it as a double integral, rewrite it as an iterated integral, use the fundamental theorem to get your answer. 3-step process. And all 3 steps are critical here. Okay. All right. Now, I want to remind you some things we've already talked about, but important. Again, very often students want to just take an application question and just immediately write it as an iterated integral. Why can't I do that? What's the point of double integrals if I'm just going to rewrite them as iterated integrals? Why don't we just skip that step? One could argue, right? I'll remind you, it doesn't fit. If you try to make a direct argument that mass is a single variable integral like that, you're going to find yourself involved with quantities that you don't understand, that aren't naturally meaningful. And I guess you could study and contemplate and think heavily about these ideas as they come up, but it's an awful lot of effort to have to make sense out of. And for every different application, there'd be a different new quantity that you don't really understand that you'd have to make sense out of and try to persuade yourself and your reader that it behaves the way you want it to. This is not strategically plausible, right? So you cannot skip the double integral step. It's just not a valid argument. Gotta write it as double integral first. And I remind you further, it's very important that double integrals be described as Riemann sums because that's what you really connect with when you do an application. If you're adding up a bunch of pieces of mass, that's not volume. Mass is not volume. Those are different things. It's not at all clear that those are the same, but mass is immediately understandable as a Riemann sum because mass, we have physical intuition for it. The whole is the sum of the parts, right? If I have a lump of clay that has a certain mass, if I break it into 2 pieces, the individual masses of those pieces adds up to the original whole because that's how mass works. Okay. All right. So be sure that you don't accidentally make these arguments here. They don't make any sense. Good news, all you got to do to avoid that problem is just always write your application as a double integral, then to rewrite as an iterated integral, which, by the way, rewriting as an iterated integral, this theorem right here, no problem. And then you can plug and chug to compute. Let's see one in action. Here we go. We're going to compute a mass. By the way, notice that this is the question that we looked at previously where we attempted to write it as an iterated integral and it crashed and burned and we found ourselves talking about nonsensical ideas of mass per unit width and what does that even mean. So we have previously attempted and failed to solve this problem. Okay, well, let's try this differently then. Step one, I'm going to rewrite my question as a double integral. And now, just to be explicit and thorough about how that works, I first argue that mass is an accumulating quantity. The whole is the sum of the parts. You can chop it up into little pieces and add those up. I then argue that on each little piece, knowing the density as mass per unit area, I can say mass is mass per unit area times area. Perfect. No problem. Nothing weird. And then, lastly, I can say, oh my gosh, check it out. This is exactly the Riemann sum that is the definition of this double integral. Okay, so kind of a little three-step process, but in practice, day in and day out, once you've seen this done a bunch of times, you're probably just going to write down just that, and that's fine. I think it's pretty clear that this is an abbreviation of that, and so anyway, it's fine. Everybody happy with that? Okay. Next, part 2. And again, following my roadmap here, right? Step 1, write it as a double integral. Done. Step 2, rewrite the double integral as an iterated integral. Again, it's a recopying thing. It's a citing of this theorem. Really hardly anything to that on these rectangular domains. Gotta love it. Double integral, iterated integral. Notice, very importantly though, the range of values for x on that outside integral, the bounds for the x integral are, well, literally the range of values of x on the rectangle that I'm doing this integral over. That's important. And then likewise, the bounds for y are the range of values of y on our integral. That also equally important. Is everybody happy with that? Alrighty. And then step 3, plug and chug. And so now we've already done this kind of thing. We know how to compute iterated integrals. You start on the inside. You realize that for the purposes of this integral, delta is a single variable function. Remember that x, the variable further to the outside, is to be treated as a constant. And so this integrand here, while at a glance you might think that for the purposes of that inside integral it's a function of 2 variables, no, x is a constant, and that is and should be treated as a function of 1 variable y. And single variable calculus. And then likewise the outside integral. Is everybody happy with that part? Okay, so 3-step process. Again, application to double integral to iterated integral to answer. Now, let's talk about the course policies here real quick. When you are doing a double integral type problem on the exam, in particular, if the question gives you an application, why am I in gray? That's boring. If you start off with an application question that you want to answer, and the question asks you to compute it all the way out, right? So in other words, the full step, you've got to give me all 3 steps. I need to see that double integral there. If you don't put that double integral, I'm just saying, just FYI, if this is missing, and the very first thing that you write down is this iterated integral, well, I'm sorry, that makes it look like you're trying to make this argument, and this argument doesn't work. So your argument is simply not valid. Does that make? I hope everybody understands. I know it seems persnickety, right? But it's very important to document your understanding, your very important understanding of the actual argument by documenting, indicating in your argument each of the critical steps, and this is a critical step. So You've got to give me the double integral, and then you've got to rewrite that double integral as an iterated integral before you start plugging and chugging. Okay. All right. Okay. Now, real quick, let me come back up here for a second. You'll notice that when I made the step 1 argument here, I did it with Riemann sums, explicitly written as Riemann sums, to emphasize what I consider to be a really important point, and again, not just for sort of ivory tower mathematician reasons, that integrals are Riemann sums. I do think that's really important. In practice, day in and day out, it is a little clunky to write them down, and so it eventually is kind of understood that, look, this is going to turn into that, so, it's actually kind of okay to write it that way in the first place, even sort of earlier, just as a shorthand, and the case could be made this is a little sloppy, but everybody does it. And everybody knows what everybody means as everybody does it. So it's fine, it is convenient, it is ubiquitous, so I encourage it, right? So rather than write this whole thing with the limit and the summation, etc., I think it's perfectly reasonable to write that. And as previously noted, it's also perfectly fine just to do that. Okay. The point here, though, is that this shorthand, this integral shorthand notation is convenient. And so I want to show you in this next example sort of an extreme version, a more elaborate version of why integral shorthand can be really convenient. So there's a little application problem. I'm going to build a wall. And the motivation for this example was when we were building our house out in Hillsborough, and the design had a wall that's about 6 feet tall, and it's actually more than 10 feet wide, but I wanted a nice round number, that is made out of stone, right? And the thickness, if you will, of the stone wall is not constant. It varies. It's thicker in some places and thinner in some places. Okay, well, that wall is made out of stone. Stones are heavy. They're on the ground. They're supposed to be a part of the wall. Somebody's going to have to pick up those stones. And again, that's a lot of stones. You're picking them up a significant height. There's a lot of work being done. Now, this is ignoring the skilled labor aspect of it, of the mixing of the grout and the, et cetera, et cetera. We're not going to worry about that part. But just bare bones, just the mere lifting of the stones from where they are on the ground up to where they will be on the wall. How much work does it take to do that? So, anyway, here's the idea. Work is an accumulating quantity. The total amount of work is the sum of, each of the individual little pieces of work representing each of the individual stones that I have to lift up to height. So that's that first step. Now again, notice I'm using this integral shorthand. That's actually a developing, heading towards a Riemann sum, but I'm using integral shorthand. Sure is handy. Okay. Next, let's ask the question, how much work does it take to take a stone that's down here at ground level and lift it up to where it needs to be, wherever it's going to be on the wall? And let's suppose it's going to be at the point x, comma, y. Well, work is force times distance. Notice that the distance here is y. The force, how much does that stone weigh? Well, that stone weighs some amount. I'm going to call that a differential amount, because in the limit, we know there's eventually going to be a limit. As I slice finer and finer, these little itty-bitty differential pieces of stone will weigh less and less and approach zero in the limit as I do the Riemann sum. So that's so we say dF because it's a differential. Is everybody cool with that? Work is force times distance. Okay, what's the force? How much does this little piece of stone weigh? Well, check it out. I have a density given, right? And this is weight per unit area. So I make the usual argument that weight is weight per unit area times area. That's all that's going on there. Is everybody okay with that? By the way, I mean, depending on the nature of the question, if it's given, sometimes you need to, in a question, mass is involved and also weight, which is a force, is involved. And tragically, they're not the same thing, right? We kind of conflate them. We talk about the surface of the earth. People talk about, how much do you weigh, whatever. That's a force. That's not a mass. Right? So anyway, sometimes you have to convert mass to force or vice versa, and that's it's a little physics thing. It's F equals ma. The gravitational acceleration at the surface of the earth is a number called g, and so we would write F equals mg, but that's a physics issue that I don't want to bog us down in. Okay. All right. And so now, check it out. Double integral. So I used this shorthand notation, this integral shorthand, as I developed my Riemann sum, but now that I've got an actual Riemann sum, it is an actual double integral. And now step 2 of the problem, turning the double integral into an iterated integral, is no big deal. The x bounds are 0 to 10. The y bounds are 0 to 6, because that's how my rectangle looks. And then it's all over with the plugging and chugging. And again, y'all can follow those details. Is everybody happy? Okay. All right. So we've focused our attention on the question of computing, adding stuff up over rectangles. The examples we've seen so far have been rectangles. What if you have a domain that's not a rectangle? For example, maybe you want to compute the volume under a graph, but in particular, just the volume that's sitting over not a rectangle, but over some weird shaped domain like this. How would I compute that volume? Not a rectangular domain. Nothing we've done prior actually technically applies here. Everything we've done assumed a rectangular domain, so it kind of feels like we need to start over from nothing. Here's the good news. Practically everything in the previous argument actually does work. It's just a little micro detail that has to be changed. But for example, the whole of the volume is the sum of the little slices of volume. That's clearly true. It doesn't matter. If you have a loaf of bread, the volume of the entire loaf is still the sum of the volumes of the slices. I mean, it doesn't matter what the shape of the loaf is. So that part's fine. This volume of a slice, how much volume is in that slice, is still no problem. This cross-sectional area times a thickness that is still a little piece of the y-axis. No problem. How would I compute this cross-sectional area? Well, this cross-sectional area that I need is still the area under a curve. I can still compute that area under a curve with an integral in the x direction. Everything that we're doing here is exactly like what we've done previously with the rectangular domain. It all is working just fine so far. There's only one little detail that's different in the iterated integral that we'll get by doing this, sort of modified slicing process. And that one little detail is that if you look at this x integral, keep in mind our x integral, is like this. We're computing this cross-sectional area here. In that x integral, the lower bound, where that lower bound is, well, that lower bound, you're going to start that x integral at a point there, that will depend on y. Because, just check it out, if you moved this over, if you had a value of y over here, right, and then you'd have a little slice and everything, and that point right there would be the point where the x integral would start, and that point, its x coordinate would be over here, not over there. So different y's give different x bounds. Everybody see that from the picture? Now, let me say that a little bit differently. Different y's give different x bounds. Another way to say that is that the inside bounds are functions of the outside variable. Right? So the inside bounds, the x bounds in this case, depend on y and are functions, therefore, of the outside variable. This is a general rule. It doesn't matter which direction you slice. You could do dx, dy like I did here, or dy, dx going the other way, or the variables can, instead of x and y, they can be called p and q, whatever. It's all good. In all cases, the inside bounds are functions of the outside variable. Okay. All right. Now, this is a hard picture to draw. If you don't believe me, give it a shot. Tricky, right? To make it look nice. We don't want to have to draw pictures like this every single time that we want to compute, either a volume or whatever other application we might actually be interested in. The three-dimensional picture is artistically challenging. So here's the good news. Notice that in the discussion of how to compute these bounds, right, where do these inner bounds come from? Notice all I really needed was to look at values of y, look at points on sort of the edge of our domain and see what their x coordinate was, and notice the entire conversation is happening entirely in the xy plane. And verticality, how high, this doesn't come up at all in the bounds question. So the good news then is, instead of drawing a three-dimensional picture like I have there, I can instead just focus my attention on just the domain itself. Just the domain in 2 dimensions. I don't need to draw height. It's got nothing to do with finding bounds. And I can make these same arguments that these bounds that I'm interested in, right, these bounds correspond to, well, they're going to be the x coordinates in this case of certain points that are on certain curves that will have certain equations. And then keeping in mind that what I'm interested in is I'm trying to find, I wanted that in the highlighter mode. What I wanted to find are these bounds. I can just solve in those equations for the bounds that I'm interested in. That's going to be our big picture strategy. I got a bunch of examples to follow, but does everybody kind of see the big picture strategy before we get into the details? Okay. All right, let's do one. So, Now, I've been asked here to compute this double integral. Before I get into computing this double integral, I want to recognize something weird about this question. We're kind of starting partway through the question. Right here in the statement of the question, it gives me the double integral that I want to compute. Let's go back to our diagram, our sort of strategic diagram here. And remember, most of the time, we have an application, and our first step is to turn it into a double integral. Not so in this case. In this case, I've just been asked to compute a double integral. Why do I want to compute this double integral? I don't know. Maybe I'm computing the value of some economic object, or maybe I'm computing the amount of mass of something, or the amount of work it takes to do a certain task. Whatever. It doesn't really matter what the application is. We've been asked explicitly about a double integral, and so all we have to do is worry about how to turn it into an iterated integral, and then the actual computation of the iterated integral. Well, yeah, okay, there's that last step as well. Okay, but we don't need to worry about this part in this case. Okay, so yeah, double integral. We've got our domain. Domain here is given to be a triangle with certain vertices given. The triangle is thus this right here. I got to figure out how to slice this up. How am I going to slice this up? Well, I got to decide which order I'm going to do my slicing. In this case, it kind of doesn't matter. Arbitrarily, I'm going to do dy on the inside, dx on the outside. No reason. Just let's try it. Let's see what happens. And so as I slice, question 1, I need to know what the x bounds are. Well, sometimes the fish just jump in the boat. In this case, x pretty clearly goes from 0, the x coordinate of that point, to 1, which is the x coordinate of that point. I can see it right there in the picture and the givens of the question. So x goes from 0 to 1. You buy it? Everybody's happy? Okay. All right, now where it gets trickier. Now we're going to fix a value of x. We're going to look now at that particular slice. I can see that y is going to go from some starting value to some ending value on that slice. What are those values? Well, again, sometimes you get lucky and the fish just jump in the boat. This lower bound for y, I mean, I can see it right there in the picture. It's obviously 0. So my lower bound for y is 0. But let's suppose you didn't have that intuition. Suppose you, let's follow the process. Algebraically, how do we get that? Well, we get that process by recognizing that this lower bound that I'm interested in corresponds to this point. That's the point that dictates that lower bound. That point, for every value of x, is on this curve, which is the curve connecting those points, for which I can do a little bit of algebra and find the equation of the curve is that. Right? So remember, our process is bounds come from points which are on certain curves that you can identify. You can write down the equation, and then you can solve that equation to get your bounds. So I just need, apparently, to solve this equation to get my bound. And a quick reminder, it's easy to lose track as you have a bunch of stuff going on, but keep in mind right now what I'm trying to figure out is a y bound. Looking for a y bound. So in this equation I need to solve for y. And well, okay, yeah, but sometimes again the fish jump in the boat. Solving for y in that equation is already solved for, no effort required, and that's where this lower bound of 0 comes from. Does everybody see the process? Slightly harder. Second example. Whoops, I do need to keep that value of x fixed. Okay, so now how do I get my upper bound for y? What's that upper bound for y? Well, it comes from looking at our slice. The upper bound from y comes from that point right there. That represents the last of that slice. That point is on that curve, which, given the givens, has that equation. Now again, easy to lose track of what I'm doing. Quick reminder, I'm trying to find a y bound. So I want to solve for y in this equation. And again, now lucky break, solving for y happens to be easy in that case. Notice it's allowed to be a function of x because x is the variable further to the outside, so that's okay. It's supposed to be a function of x, as expected. And so we get, for our upper y bound, we get x. Everybody buy that one. The point here, of course, is the process, not the result. Okay. All right. And as predicted, we have an iterated integral where the inside bounds are indeed functions of the outside variable. Happens to be an easy, boring function of the outside variable in the lower bound case, but that's fine. It's okay to be a boring function. Okay. All right, and then plug and chug computation, blah, blah, blah. Y'all know how to do that. Okay, now let's do it the other way. Same domain, same triangle, same double integral that I want to compute for reasons that aren't given but don't matter because we don't have to, the question just says to compute this, so okay. All right. Now though, slicing with dy on the outside. Okay, our y slice starts there and ends there. So again, I need to find, for my lower bound, I need to know what's the value of y on this first slice. Easy, no problem. I just stared right at me. It's clearly 0. Last slice, I need to know the value of y to find my upper bound. Again, that's a point that was explicitly given. I know exactly what the coordinates of that point are. That upper bound for y is 1. Lucky break. Everybody happy? Okay, we'll see other examples where we won't get so lucky. A couple of minutes. Now we're going to fix a value of y. Y is now fixed. We're going to look at our slice there. That is our y slice. That gives us now a range of values for x. How do I find this range of values for x? Okay, well, the lower bound for x comes from this point, which is on that curve, which has this equation. Solve for x in this equation. X is that. Notice it's a function of y. No problem. It's supposed to be a function of y. Y is the outside variable. It's allowed to and supposed to be a function of y. And so that lower bound for x is y. Everybody happy? Okay, upper bound for y. Upper bound for x. It's easy to get them switched. Be careful. Let's take my mistake there as a nice little demonstration of how easy it is to mess that up, right? So super careful. We're on our inside bounds. X is what I want to find the bounds of. So I need to find that upper bound. Well, that comes from that point, which has that equation. Which is on that line, which has that equation. Solve for x. Again, easy to solve for x, and upper bound is 1. Okay, so now you've got your choice then. When you answer the question of how do you compute this integral, you could compute this iterated integral, or you could instead compute that iterated integral. Take your pick. In this case, I guess I have maybe a ever so slight preference for the orange one because I see more zeros. I like zeros, right? So I'd probably lean orange, but if you wanted to do the purple, that's fine. It's cool. It's fine. Doesn't matter. All right. Okay, let's see more examples. Here, another region where I'm going to slice both ways. Here, it actually is going to matter which way you slice. You know what? I got ahead of myself. I wanted to make one other point. Notice, as previously promised, even though I've switched the differentials order, notice the bounds do not just go along with it, right? These bounds here are not the same as those bounds there. So this whole story of, you just move the differentials and the bounds just into out to in, knock yourself out. No. Just doesn't work. Except in the weirdly convenient special case of a rectangle that we initially saw. But in general, it doesn't work. Okay. All right. So let's do this one now. We have two curves given, y equals x squared and y equals 4. So those are two curves with a domain that we're interested in is this region in here that's bounded by those two curves. Now I do want to say a couple of quick words about the language here. Bounded by it has a double meaning. It means for one thing, that this region that I'm interested in, the boundary includes those two curves. But notice this region up here, its boundary includes both the green curve and the blue curve also. How do I know that that's not the region that we're interested in here? And that's the second part of the meaning of the phrase bounded by. Bounded by also means bounded. It means that it doesn't run off to infinity in any direction. It means you can put a fence around it. You can fit it into a box. It's entirely contained. Bounded is the word that we use to describe such a thing. And among the regions that we could consider here, given these two curves, this is the only one that's actually bounded. Does everybody see that? So this is going to be part of questions that you're going to see and encounter in this class and others. You're going to need to be familiar with how to interpret that word bounded by, and remember it's part of your job as the answerer of the question to interpret that correctly. Okay, so here we go. Let's slice in a couple of different ways. We've got, first of all, going in the doing our, let me pick a better color, doing our X slicing on the outside. Notice the fish did not just jump in the boat here. I was not given initially what these points are. This point here, not given. So here we're actually going to have to do some work to figure out what this lower bound is. Now, it's not a big problem. For this bound, yeah, that's the point. What curve is this on? It's actually on two curves. That point is on both of those curves. So when I solve, and keeping in mind, I'm trying to find X bounds here. Let's see here. You know what? I'm going to go back to green here. Trying to find this lower bound. That is a bound for X. I need to solve for X in this pair of equations. I should do that in orange. Solve for X in this pair of equations, and I've got to do a little bit of algebra. I've got to think it through and notice that the X that I'm looking for, well, X squared is Y, but Y is 4. That means X squared is 4. That means the number I'm looking for is either negative 2 or 2. Now I have to look back at the picture, and from the picture, I see that the coordinate I'm looking for here as my lower bound, the picture tells me it's negative. So my choices of negative 2 and 2, the picture is how I distinguish that I actually want negative 2 for that lower bound. Everybody see that? Analogous process to find the upper bound. The upper bound for X, I'll be quick about it. The upper bound for X comes from that point, which is on these two curves. Oh, cool, same two curves. So in this pair, again, I need to solve for X because I'm looking for an X bound. Again, I get negative 2 or 2 to choose from. The picture tells me that apparently here for the upper bound, I want the positive one, and that's why I pick positive 2 there. Is that cool? Alrighty. Inner bounds. Now, so again, we fix a value of X. We look at that X slice. The lower bound that I'm interested in comes from that point. That point's on this curve. That curve has that equation. Now I'm confused. It's easy to lose track of what you're doing. I have to remind myself actively here, X is fixed, and I'm trying to find a value of Y. I'm trying to find the lower bound for Y. So in this equation here, I need to solve for Y. Oh good, lucky break. It's already been solved for. Isn't that nice? Notice as appropriate, it is a function of X. That's cool. It's supposed to be a function of that outside variable. Is everybody okay? It's getting pretty repetitious, I know, right? I want to make sure everybody's very clear on the process before we start just kind of assuming that. Okay. All right. Upper bound. Again, X fixed. Looking at that slice, the upper bound comes from that point on that curve, which is that equation. Again, reminder, we're solving for Y. Again, we get lucky. It's easy to solve for Y. y upper bound is 4. Okay. Now, let's continue, but do it the other way. Same domain, same curve. Let's slice the other way. What's the range of values for y? Well, here's what my y slices look like. The first one is at the origin. Really no work required. What's the y coordinate of the origin? No problem. 0. Last value of y. Well, it's literally that curve where y is literally given. So again, nice easy ones. You gotta love it when that happens. Very convenient. Okay, now we fix a value of y. We look at that y slice. Now we want to understand the values for the x bounds. How do I solve for x here? Well, this lower bound is on this, oh, come on, stylus, has this equation. Sorry, that curve, which has that equation. Again, really easy to get confused here. Remember, and for emphasis, I'm going to switch to purple here. I'm trying to find x bounds. In this equation, I need to solve for x. This is what a lot of students get wrong. A lot of students will say, that curve is x squared. And a lot of students would put an x squared here. That does not make any sense at all. You can see why students would do it. Oh yeah, the point is on that curve. The curve is, again, high school encourages students to be sloppy about these kinds of things. This curve is not x squared. This curve is y equals x squared. The bound isn't just whichever side of the equation looks more interesting. The bound is you got to solve for the correct variable. So I have to solve for x in this equation. Everybody good? How do I solve for x? Okay, well, let's take the square root of both sides. So I have plus or minus y. Ooh, wait a minute. Which one is it? Well, keep in mind, I'm looking for a lower bound here. And I can see from the picture, that one's negative. So when I solve for x here, I get the negative square root of y. Everybody happy? All right. Okay, and then likewise, and again, super quick, the upper bound comes from that point, same curve, same issue of solving for x. How do I solve for x? I got to take the square root this time, positive, because picture tells me, thank you, picture, that upper bound is positive. Cool. All right, so that's the process. I'm going to start moving more quickly through these now because we've seen the process painstakingly, carefully, quite a few times now at this point. So moving a little faster. Here's a relatively hard problem. There's a landmine on this. The purpose of this example is to point out the landmine. We got a triangle, various corners given. Cool. We're being asked to compute a double integral. Why? Who cares? Doesn't matter. There's some application. Not our problem. We've just been asked to compute a double integral. Don't worry about where it came from. And now let's look at our y bounds. Y goes from 0 to 1. Cool. And then for a given value of y, x is going to go, well, from there to there, which means from that point to that point, and I can look at each of those points, think about the curves that they're on, find the equation, solve for x, the same process you've seen it a million times, and you get x goes from there to there. Y'all comfortable with that? Okay, on the other hand, what if I slice the other way? What if I do dx on the outside? Well, x, tempting to say x goes from 0 to 2. Turns out that's a problem. Because if I say x goes from 0 to 2, then when I'm looking for my y bounds and when I'm trying to find that upper value of y, right, my y slices kind of look like this. My upper bounds for those slices are those points which are not just on a single curve. They're on two different curves. I can't solve for something in two separate equations at the same time. It just doesn't work. Everybody see the little landmine there? It's a nasty little problem. That's annoying, but easily fixed. No problem. What I'm going to do is, instead of having x go all the way from 0 to 2 all at once, I'm going to take a two-step process. First, I'm going to have x go from 0 to 1. Just 0 to 1. And then subsequently, I'm going to look at x going from 1 to 2. Now, on each one of those, finding the bounds for y is no big deal. To find the value of y here, let's just focus on just the upper bound. As x goes from 0 to 1, notice my upper bounds for y are all on a single curve. Single equation, easily solved. Bam. Everybody good? And then on the second half, right, looking over here, what's the range of values of y? Keeping in mind this has x going from 1 to 2. Well, for those values of x, my upper bounds for y are all on that curve, which has an equation which you can solve, and you get that. Everybody see how that works? So, careful. And you got to watch out. Now, I think we would all agree that given our options, we'd rather do this one, not that one. Right? Who wants to do twice as many integrals? That doesn't seem prudent. Right? All else being equal. Of course we want to do the easy one. Of course we want to do just the one, not two. How can we anticipate this in advance? And here's my rationale. The way I like to think about this is, think about your outside slicing process. Here I have y slices. Y slices look like this. Nothing weird happened there. But I claim something weird does happen if you do your x slices on the outside. As you do your x slices, I'm going to say we sliced through a corner as we were doing outside x slices. The fact that we sliced through a corner ultimately kind of was the problem. That's what allowed our y upper bounds to switch from that curve to that curve. Right? The jump between the dark blue and the purple happened where those curves intersected, and curves intersect at corners. So the strategy that I encourage is try not to slice through corners, right? And if you do your x slices on the outside, then you will at some point slice through it. Oh gosh, slice through a corner. That is your tip-off. That's your sort of like at a glance, intuition for, yeah, I think this is going to be bad. You buy it? Okay. Oh, let me go back. There was a lesson on this one as well. I was in a hurry. I kind of glossed over. Which of these do we like better? I have a preference. Myself, I like this one. I don't like this one because I don't like square roots. And here's what's worse. You might say, well, they're just in the bounds. It's just what you're going to be plugging in, right? But no, these square roots are bounds which get plugged in to the inside integral. Therefore, they are part of the integrand of the outside integral. So you're going to be doing a dy integral at the end. And that dy integral looks like it's going to have square root of y peppered in variously throughout that integrand. And those are notoriously inconvenient, undesirable integrals. Right? Everybody with me? So, how do we avoid that problem? How do we, again, you can write them both down and, then scope them both out while you look at them both directly. But there's a certain amount of effort that goes into writing these iterated integrals. What's the tip off? Can I see it coming in advance? And my idea here is the reason that these square roots happened is because I had to solve for x in this equation here. I had to solve for x because x was the inside variable. So my idea is, as you're trying to decide which of these orderings of the differentials you'd prefer, ask yourself, do I want to solve for y in the various equations that are involved here? And I think to myself, yeah, sure, I'd love to solve for y. I don't even have to do anything. That's effort-free. I like solving for y in this case. Do I want to solve for x? Ew. No, I don't really want to have to solve for x. Oh man, so not only is there a little effort involved, but I can see it coming. I don't even have to solve for x. I can see that it's going to involve square roots. And I know already that I don't like square roots. Right? So the variable whose differential you put on the inside, try to choose it as the one you'd like to solve for, given your options. Okay. All right. Okay, another example, and I think, I think we can get this done. So sometimes the domain is actually not given. This is not that big a deal, but I just wanted you to see one of these walked through. So here we have a paraboloid, and then here we have a plane. The question that I have is to find the volume in between those. That's this kind of, oh, come on, man. This gray region here that I'm highlighting in yellow. So there's what I want to compute. Certain parts of this are very straightforward. I'm going to view this volume as the sum of a bunch of little French fries. French fries are height times the area of the base. Boring. Right? I guess there's one little quick little detail I'll point out, that finding this height here, that height is not explicitly one of the things that's given. But we have a picture. The picture makes it pretty clear that what I'm looking for is the difference between that z-coordinate, which I'm going to call z2, and this z-coordinate. This is z-coordinate here. I'm going to call z1, and the height is just z2 minus z1. Is that cool? Okay, so now, but let's talk bounds. What are the bounds for this integral? This is easy to mess up. A lot of students argue as follows and say, well, the bounds, here's going to be my domain down here. The bounds are going to come from that perimeter of the domain. That perimeter comes from this kind of, I don't know what you'd call that, lip, I guess, of the bowl that this is. So I need to find where that intersection is. That's the intersection of this, highlighter. The intersection of this surface and this surface. Right? And so here's where the students make a mistake. All that's correct so far, by the way. The mistake that a lot of students make is they say, the way that I'm going to find where these intersect, the way that I'm going to understand this intersection here, is I'm going to set these equations equal to each other. I see this all the time. And that's not a thing. That's not how you do anything. Setting equations equal to each other, I don't even know what that means. And I have some silly examples just for, sort of dramatic purposes, but I think we would all agree, for example, that 3 is equal to 3. And I think we would all agree that 7 is equal to 7. If I want both of those to be true at the same time, do I set 7 equal to 3? No, of course not. That's silly. Right? So please do not set equations equal to each other. It just doesn't make any sense. Right? So what do we do instead? The idea is, keep in mind our goal is to understand certain points. I want to understand this curve here in particular that makes the boundary of our domain. The points there have the feature that the height up to the plane which is the z variable in the equation of the plane, and the height up to the paraboloid, those are the things that need to be equal. I don't set an equation equal to an equation. I set a variable equal to a variable. You set those two. You set z1 equal to z2. Does that make sense? And does everybody see the difference there? Now, at this point, it's just an algebra problem. You can solve for those z's. The first z was easily seen to be this. Little algebra gives you the second z to be this. And yeah, you got to go through. And by the way, I hope everybody remembers how to do complete the square. If you haven't thought about completing the square in several years, I will bet might be the case. As certainly has been the case for a lot of my students in the past. Make sure that you brush up on that skill. Completing the square is an important algebraic tool that, again, it kind of gets swept under the rug a lot, right? So you have to complete the square here. And that said, then notice you get an equation. It's just the equation of a circle, and this is how you're going to form your bounds for that integral. Okay, so this is a good stopping point. We will stop right there. And see y'all later. Have a good one. Right. Have a good weekend. And don't forget, we have an exam on Monday, first exam of the term. It's right here, our usual class period. Do make sure to be on time. We will be starting as fast as we can after on time. And good luck studying. And don't forget about the TA office hours. They could be really helpful. Right, 1 to 3 this afternoon for Yupeng, and I've forgotten what Michael's hours are, but I think he has some. Yeah, he has some weekend hours posted on the site.